Hi, everyone. Welcome to the 68th online Spintronics seminar. It's a great pleasure to introduce today's speaker. Professor Yayoi Takamura received her bachelor's degree from Cornell University in 1998 and her master's and PhD degrees from Stanford University in 2000 and 2004, respectively, all in the field of materials science and engineering. She was a postdoc researcher at UC Berkeley with Professor Yuri Suzuki in the Department of Material Science and Engineering before joining the Department of Material Science and Engineering at UC Davis in July 2006. Her research focuses on the growth of complex oxide thin films, heterostructures, and nanostructures, and the calculation of the novel functional properties associated with their interfaces. Professor Takamura is a recipient of the NSF Career Award, the DARPA Young Faculty Award, and the 2020 College of Engineering Mid-Career Research Award. So without further ado, Professor Takamura, please go ahead with the talk.
Okay, great. So thank you for Tailor and Shin for inviting me to give a seminar on this seminar series. So it's a pleasure to talk to you about some of the work that my group has been doing over the last, I guess, many years now. And I wanted to sort of give sort of an overview of what we've been doing, trying to tailor both ferromagnetic and antiferromagnetic spin textures in complex oxides. And so before I begin, I wanted to acknowledge, the students and collaborators who helped with this work. So, members of my research group. So the main contributors are shown here in the center. So Michael Lee, Rajesh Chaptakar, Pei-Fan Liu, Tom Win, and Binzi Lee. But I also want to mention that this is a highly collaborative work. So we worked with the Center for Nanophase Material Sciences at Oak Ridge National Lab, the Advanced Light Source at Lawrence Berkeley National Lab, as well as NTNU, the Norwegian University of Science and Technology. And also want to acknowledge funding from the NSF. And I also have other funding on other work in my group through an EFRC center out of UC San Diego. And so just to give you an outline, sort of where, sort of what the outline of the talk, so I'll give some introductions and talk about, a little bit more tutorial style on the photoemission electron microscopy technique, which is how we'll actually image these spin textures, again, both in the ferromagnetic and then antiferromagnetic materials. And then I'll go in and talk about 3 different examples of these spin textures, again, the ferromagnetic, antiferromagnetic, and then coupled systems together. And so when I talk about different complex oxides, so what I are usually referred to are these multi-component oxides, and so they're going to be complex in terms of their chemistry, so that there's lots of different elements involved, and also in terms of their structure. So more complicated structures. So some examples are shown here is the spinel, the perovskite, and the fluorite structures. And so these materials have very fascinating functional properties. And there's lots of different stimuli that we can use in order to really tune their properties. And so in particular, my group has over the years focused on these perovskite oxides. So these are sort of generally ABO3 chemical formula. And if we look at this color-coded periodic table, what we find is that there's many different elements that we can choose from the periodic table to sit on these different lattice sites in the material. And so that's one of the reasons why we can have a very large range of different functional properties. And so we can also do different chemical dopings on the different sites. So we get these highly tunable properties ranging from superconductivity to optical properties and different magnetic properties. And so my group has mainly worked on ones which involve the first row transition metal elements in the B site. And again, because those are our magnetic elements. And so in particular, I just want to introduce the 2 materials that I'll focus on for this talk. So the first one is a lanthanum strontium manganese oxide. So it's out of the manganite family, and so I'll refer to it as LSMO. And so it has a very complex phase diagram. So the diagram on the right shows temperature as a function of the strontium concentration, all the different types of structures and magnetic phases that you can have. So they range from ferromagnetic metals, and various different forms of antiferromagnetic materials. And for this talk, we'll focus on the 30% doping, so which is squarely in the ferromagnetic and metallic regime. And so these materials are, of interest. The Curie temperature is slightly above room temperature. At low temperatures, it's a half metal. It also displays colossal magnetoresistance. So it's been a very heavily studied oxide in the field. And then what we do is then we've also looked at, just switching out the B-side element for iron. So one next door on the periodic table. And what we end up with is an antiferromagnetic insulator. And at least at this 30% strontium doping, then it has a nail temperature, which is actually somewhat similar to the Curie temperature of the manganite. And so that was sort of one of the motivations that we had for sort of looking at systems where we look at these multi-layer structures. In some of the work later, I'll also show lanthanum manganese oxide, which without the strontium doping, the only difference is that it has a much higher nail temperature. And so for everything that I show, all these samples will be grown by pulse laser deposition, and then on 001 oriented strontium titanate substrates. And for this talk then, not only do we care about thin films, but then we wanted to pattern these materials into nanostructures or microstructures. And so the way my group has been doing it for the past 15 years is actually using, rather than an etching-based technique, but actually using a flood argon implantation in order to define our structures. So basically what we do is we take our thin film, we pattern using electron beam lithography, a chromium hard mask, and into the design of whatever pattern that we want to result in. And then we flood implant the whole sample with argon. And so the choice of argon is just that it's an inert element, so it's not going to chemically dope the material. And what happens is that where the film is unprotected, then the argon ions come in and actually amorphize that part of the film, but the chromium layer is thick enough that all the argon ions actually get stopped by the chromium layer, and then the fin underneath it then is unaffected. And so when we remove the chromium afterwards, what we end up with is basically these magnetic structures then surrounded with a non-magnetic matrix, right? So it's not actually freestanding pillars, it is an embedded nano island, and we'll find that the regions which have been implanted with argon actually swell a little bit. And so we actually see a small height difference between the matrix and the film. And to sort of show that in a little bit more detail is here some cross-sectional transmission electron microscopy image. So the implanted part of the film is on the right, the protected part of the film is on the left. It's a little bit hard to see in this image, but we still do have the lattice fringes. So this is a nice crystalline region. This is the implanted film is amorphous, right? And then here's the substrate, and we actually see that some of the damage does go down into the substrate as well, but we can have a fairly sharp, not atomically sharp interface between the protected and the unprotected regions. So again, we get these magnetic islands embedded within this non-magnetic matrix. So what we wanted to do then is the motivation are these spin textures, right? So basically different domain configurations, right? And so you can have lots of different types of spin textures. You can have chiral domain walls. You can have these Landau or vortex states, which are then controlled typically based on the shape of the nanostructures that we create. And then, somewhat recently, this concept of these fermions has become more important. And it's really these Landau vortex states that we'll sort of look at more in detail. And what we'll find is that there's lots of different parameters, magnetic parameters that we need to consider in order to understand or predict which states are going to be the the stable states that we have. So different parameters, not only is it, shape anisotropy driven, but we have to care about magnetocrystalline anisotropy because these are all epitaxial films, exchange interactions, different spin orbit coupling as well. And then just as sort of background to make sure everyone understands the technique that we're using. So in general, what I'll be showing are the use of soft X-ray magnetic spectroscopy. So I call this sort of the overall umbrella of the technique, and we'll have two different variants of it. So the first variant is XMCD, or X-ray magnetic circular dichroism. So out of the two, it's probably the more commonly used technique. And so with this technique, then we're using soft X-rays. So these are X-rays, in a few hundred to maybe 1,000 electron volts. And these are then tuned to the different absorption edges of the elements in the material. And in particular, again, for the first row transition metal elements that we're interested in, then we're looking at oxygen 2p to 3D transitions, which are then the 3D orbitals are the ones where we get that magnetism. So it's a really good way of probing then what are the empty states at the Fermi level in that in those d orbitals. And so now if we come in with circularly polarized X-rays, then the right versus left circularly polarized X-rays are sensitive or can promote transitions between up and down spin electrons. And so if we have a magnetic material, then we get an imbalance in the filling of the electrons in the d orbitals. And so we'll see that as a dichroism or a difference in the absorption between the right and left circularly polarized light, which is shown here as a spectrum in the middle for an example of vanillissimo film. And then so the actual X-ray absorption spectra on the top, and then the calculated difference between that is shown at the bottom. And so for each material, whether you get sort of a fingerprint of which elements are magnetic in the material, and you can tell is it not only is it manganese, right? So we always know that the manganese absorption edge is around 640 electron volts, but then this line shape of this particular spectrum then is tells you, is it manganese 3+ ions, which are magnetic, or is it manganese 2+ ions? And so similar, both the XAS and the XMCD spectra give you that kind of fingerprint. So it's pretty powerful technique. And then we can also do things like take hysteresis loops and stuff, because then the intensity of this XMCD is then has a cosine theta dependence, where theta is the angle between the X-ray helicity and the magnetization. So we'll be able to use that fact when we actually look at some of the images of magnetic domains. And then sort of the second variant of this technique is X-ray magnetic linear dichroism, or XMLD. And so you can see that now instead of circular dichroism, it's linear dichroism. So we're using linearly polarized X-rays. And so what we can do is sort of denoted as a searchlight effect. So we've got this oscillating linear polarization vector of the X-rays. And so that can actually then look for any asymmetry in the system, right? And so one thing that you have to keep in mind for this technique is that a priori, you don't really know which asymmetry is leading to the dichroism that you'll see. It could be, could be our orbital occupancy, could be crystallographic directions, or it could be the direction of the antiferromagnetic spin axis. And so what we hope for is that we can come up with a measurement geometry where if we have an antiferromagnetic element, so our iron ion in this case is antiferromagnetic, and so it's going to have some elongation of the charge density around the iron atom. So if we come in with linearly polarized X-rays, which are vertical, so along the long axis of that charge density, or horizontal, which is along the short axis, we'll get a difference in the absorption spectra so that we can calculate an asymmetry. And so what we'll get then is that, again, we need to carefully design the experiment geometry that we have in order to basically rule out any of these other effects. So for example, then if we're looking at one of our thin films, then we need to then change the polarization direction. So from vertical to horizontal, which will then probe along, say, 0, 1, 0 direction, which is in plane of the sample, and then 0, 0, 1, which is out of the plane of the sample. Because if we think then that our our spin axis might be lying in plane, and we want to see that, then we'll use this other geometry. And so we're along sort of the same general family of crystallographic axes. And so as an example of what the spectrum might look like, again, this is for the iron and LSFO. This is the line shape tells us that we have a mixture of iron and 3+ and 4+ valence states. And then we see that both peaks then break up into A and B peaks, which is sort of indicative that it is an oxide and not metallic iron. And then you can see that we get this sort of plus minus features for both at the L3 and the L2 edges when we do the different spectra. And so again, each source of linear dichroism, whether it's orbital occupancy, crystallographic effects, or the spin axis, will have a characteristic line shape. So if you're able to either have reference data or do some simulations, you can actually then sort of have a fingerprint of what is your source of your dichroism spectra. So if it is from an antiferromagnetic source, then this is sort of the intensity function. And so in this case, instead of a cosine dependence, it's a cosine squared dependence, right? So a different functional form. And so it separates it from the circular dichroism. And so what we want to do then is we can collect spectra. And so that's one of the things that my group does, is actually collect the spectra. We get lots of really cool information about the spectra. But then what's, again, always powerful is seeing a picture, right? And so what we can do then is use exactly that same technique, X-rays in, and what we're actually doing is collecting electrons from the sample, but we can actually collect those photo-emitted electrons with a really powerful electron microscope, right? So this is just a schematic of an example of a photo-emission electron microscope, or PEM. We use the one at the advanced light source. And so what we can do is, again, that beamline has the ability to change the polarization of the X-rays from circular or linear dichroism or linear polarized X-rays, so that we can, from one location, right, image what the ferromagnetic domains are, as well as what the antiferromagnetic domains are, again, if they happen to coexist in one sample. And again, if we've got I've got a multi-layer structure where, say, manganese is the magnetic layer and then iron containing layer is antiferromagnetic, we can actually separate out the contribution from each layer using this, because these magnetic effects are, or at least the magnetic spectroscopy is element specific. Okay, and so what you'll see in terms of images and are shown here. So again, this is that same manganese XAS and XMCD spectra that I showed you before. So what we'll do in a PM experiment is we'll tune to this energy here, just above 340 eV, where we have a maximum dichroism. So the magnetization is the strongest at this particular energy. And then we'll take images using both right and left circularly polarized light. And then we'll do a dichroism. We'll sort of do a difference divided by the total intensity. And that will give us these images here. And basically we do sort of that mathematical operation in order to remove any topographical or any work function differences from the different locations of the images, and so that we get just the magnetic information. So this is an example of for an unpatterned LSMO film, what the typical domain structure looks like for a film. And so the way that we're going to read this is we need to know always what is the direction of propagation for the X-rays. For this particular image, it's coming, sort of at an angle, right? And so regions which are black and white are going to be parallel and anti-parallel to the X-rays, and regions which are gray are going to be perpendicular to the X-rays, right? And basically follows that cosine theta dependence, and so you can have, angles in the middle. But sort of for this case where, we've got fourfold symmetry in the sample, then we expect only to have these 4 domains. We can't really tell the difference between these 2 domains, which are pointing up versus down, because they're just, the angle is still always 90 degrees to the X-rays. But that's sort of how we can determine, we can actually image determine the direction, local direction of the magnetization in these materials. And so what you can see for LSMO is that in general, we have very large magnetic domains. Again, it's somewhat dependent on the thickness of the film, but many microns in size for an unpatterned film. And so then if we want to look at the imaging that we can have for antiferromagnetic domains, so this, again, is using linear polarized X-rays. So for example, if I were to come in with linear polarized X-rays, which are vertical, right? And let's say I had antiferromagnetic domains here. So black versus white are different antiferromagnetic domains. And so what I'll find is that the E vector is either parallel or perpendicular to the antiferromagnetic spin axis within these two domains. I'm going to get this kind of local, this X-ray absorption spectra. So for the imaging, what I'm going to do is I'm going to take two images now. The two images are going to be at a fixed polarization, but now at two different energies, one at the A peak with a positive XMLD signal, and then one at the B peak where you have a negative XMLD peak. And so then again, if we do this normalization, take the, the difference normalized to the sum, then we can get our dichroism picture. And so then what we'll get is that we can sort of map out locally what these antiferromagnetic domains look like. Okay, so that would be if we had one single polarization, but then what we'll actually want to do if we want to map out in 3 dimensions what is the direction of the antiferromagnetic spin axis, we're actually going to go one step further. And so not just use the vertical polarization of the X-rays. At the PM3 microscope, you can actually change the orientation of the E vector. So I'm not just stuck at vertical, I can actually rotate it all the way so that it's horizontal. And so if we're coming in with a 30-degree grazing incidence angle, right? So then vertical at 90 degrees is completely in plane. The 0-degree one is actually meaning that the E vector is canting out of plane along that 001 direction. So we can actually map in 3 dimensions what the antiferromagnetic spin axis, where it's lying. And so what we'll get are then a series of images here. So this is going from B is equal to 0 is when it's canting out of plane, and then going to beta equals 90 degrees where it's vertical. And so what you'll see is that as we change that polarization angle, right, if we just sort of, what I did is color code a few regions of interest, right? And so if you follow them, for example, with the blue domain, right, this blue domain stays white, regardless of what the polarization angle is. But if I look at the domain, which is directly above it, the red one, right? So that one is opposite, is very different. It starts very dark, right? And it gradually gets lighter, right? And so at the, here at 90 degrees, they're actually almost the same contrast, right? And so again, we know that we have this cosine square dependence, right? So what we can do then is map as a function of that beta angle, the polarization angle, what the intensity of each region, basically pixel by pixel, we can then sort of categorize them into different types of domains, right? And that's what we have here is, and then what we find is that for all the pixels in those images, we can bin them into 4 different types, right? And so they have these different, different sort of functions as a function of the beta angle. We can compare them to that, plugging into that cosine squared dependence. And so what we can then determine is that in this case, what we have are 4 different types of antiferromagnetic domains, which differ in the orientation of the spin axis. And what we can determine is that the canting angle out of plane is 30 degrees. And then they want to, their in-plane projection is along the 0, 1, 0 family of directions in the material, right? So it's a way to really be very particular in terms of mapping out your antiferromagnetic domain. So it's a much more, I guess, laborious process in terms of being able to map out antiferromagnetic domains rather than ferromagnetic domains. Okay, so hopefully then you have sort of an idea of how to actually, how we do these measurements, and then how we actually interpret what the antiferromagnetic spin axis is doing. And so then what I want to do is go in with the remaining time and talk about, 3 different examples of our spin textures in manganites. And what I think is always interesting with these complex oxides is there's lots of different things that you see in them, which we don't see in sort of their metallic counterparts, right? And so again, what I have here is, so we've patterned these LSMO, we patterned it with our ion implanted technique. So this sort of gray region outside of all of our shapes is that implanted matrix, so it's non-magnetic, and we pattern them actually in fairly large structures at 2 microns, sort of either in diameter or in terms of the length. And I always feel that people always want to go smaller, nano, but we actually find that this micron scale is where we get some really interesting physics, and so we've focused quite a bit of our effort on looking at these dimensions. So if we look at this temperature, so 230 Kelvin, so the material is very magnetic. And we looked at different shapes, so basically sort of square, diamond, and circles. And then what I want you to just sort of always reference is the direction of the X-rays and what are the direction of the magnetic easy axes for this film. So for LSMO on strontium titanate substrates, then the easy axes are actually the 110 family directions and not the 010 family. And so what we get is what, Landau or vortex structure domains. So nothing unexpected, right? It's basically shape anisotropy is dominating at this particular condition. And even though with a diamond shaped one, it sort of looks like you only have 2 domains. But again, it's because the projection of these domains in the direction of the X-rays are the same, so we can't actually distinguish. But we've rotated the sample. We know that we really do have a Landau structure actually with 4 domains, as in the schematic. Okay, so and then the circle, right, is a vortex where you sort of see this gradation of color going from white to black in the circle. And so, but then again, I said is these complex oxides always give us some interesting things that happen. And so if we now take the same sample, right? So the data that I just showed you is on the right-hand side, so 230 Kelvin, purely in the Landau structures for all of the samples. But now if we cool it down to cryogenic temperatures, right? And again, not super cold, right? And one thing you can see is that for the square, right? So the edges of the square along the easy axis of the material, nothing happens, right? Maybe the images get crisper, right? Just because the magnetization is getting stronger, but we get some interesting structures that appear in the center of the diamond and the circle structures, right? And you can see that this center part, right, which didn't exist at higher temperatures, matches that of the square, right? And so now what we have, sort of as shown in this these schematics, is that we actually have a superposition of 2 different Landau structures, or a vortex and a Landau on top of each other, right? So the edges of the perimeter, right, then we have shape anisotropies that's as sort of dictating what the edge of the nanostructure should look like, but magnetocrystalline anisotropy, right, is dominating in the center. The magnetization wants to lie along the easy axes, right? And so we see that as we cool the temperature, that then this, we really see the dominance of the magnetocrystalline anisotropy at low temperature, and it goes away at high temperature. And so what we could do is actually, so we thought, okay, those are really nice images. Can we actually be more quantitative, right? Can we actually understand, how is the magnetocrystalline anisotropy changing as a function of temperature? So we wanted to do some more analysis of these domains. And I guess here I've actually switched the order. So now high temperatures on the left, low temperatures on the right. And what we kind of went back and forth with different ways of actually analyzing this. But what we did is we decided to take a profile in terms of a circle in the center of the nanomagnet. So here for the square one at low temperature, right? And we know that it should be a Landau structure. So 4 distinct magnetic states. And that's what we see. So we get the gray, white, gray, black, right? So a step function that we expect. Right, and then we went to the circle one. And first we start with the circle at high temperature, right? And I said that we should see a cosine dependence as the magnetization circles around, and you can see that's what we have. We have a cosine dependence, right? And then we went to the circle at the low temperature, right? And so here, just by eye, you could say, oh, this is a Landau pattern. It should have just 4 colors, right? But what we've noticed, though, is that if you look carefully, right, these regions where it should be gray, uniformly gray, are actually not uniformly gray, that they're actually sloped. And what we could actually do is actually reasonably well fit that gray region to a sine or a cosine function, right? And so we could then deconvolve the actual raw data, right, as a superposition of our step function, right, which is in blue, right, and then the sine function or cosine function, right? And so what that told us is even though by eye it looks like we have a Landau pattern, what we actually have is still this superposition of this vortex sitting on top of this Landau pattern. And so Michael Lee decided to call this a vortex fraction, right? So the vortex fraction was basically the ratio of the amplitude of the sine function over the amplitude of both the sine function and the step function, right? And so what he did then is he took those functions as a function of radius, right, for all of these different nanostructures, and then he did that analysis as a function of temperature. And what he did then is that then he went into mu max 3, right? And then actually did some simulations in order to get mu max to match up with the same, basically with the same type of P images and this vortex fraction. So he was using this vortex fraction as sort of his parameter to compare our experimental data to the mu max 3 simulations. And then what he found is that the only way to match things up was actually to have a very sharp radial dependence of the magnetocrystalline anisotropy, right? So again, at the edges is where we saw the shape anisotropy driven dependence, and then in the center is where we had that magnetocrystalline anisotropy. So we basically went from very high, highly anisotropic material to basically at the edges no crystallographic direction dependence. And then what we could do is then also look at the temperature dependence, right, of this magnetocrystalline anisotropy as a function of temperature and compare it to our literature data for LSMO. And so basically they have the same temperature dependence. If we normalize them to what happens at the lowest measurement temperature that we had, which was 30 Kelvin, then we actually see that they overlay very nicely. So basically what we could do is that, say that, within these nanostructures, right, we actually are getting bulk, or close enough to bulk like magnetocrystalline anisotropy, but we could also then map them, right, locally, right, with sort of 100 nanometer sort of spatial resolution, really what these magnetic parameters, we're doing as a function of temperature, right, and as a function of position within the nanomagnet. Okay, so that was then when we had our ferromagnetic materials, and then I want to show you what happens when we deal with the antiferromagnetic materials. And antiferromagnetic materials are always interesting because there really are no, typically there's no magnetostatic energy. So one usually thinks, if I pattern an antiferromagnetic material, it shouldn't matter how I pattern it, right? But I'll show you that we actually do see some shape anisotropy effects. So the first thing I want to show you is if we have, sort of a thick film. So this is analogous to just the last example where we have 100 unit cells of LSFO or antiferromagnetic material, and then we pattern it again into 2 micron squares. And again, this is the series of images that we get as we do this polarization rotation series. And so we get a series of different types of domains, right, which all have their own beta dependence, right? And so what we can do is that then we can actually, again, pixel by pixel, map the dependence of those domains, right? And then we, again, end up binning them into 4 different types, right? So these are their dependence as a function of beta. And then we can look at where, and so one we could do is actually, again, figure out that now the canting angle out of plane is around 35 degrees. So very similar to the thin film before we had patterned it. Right, and then we can also image, basically go back to our original image, right, and then sort of map out where those different types of domains are, right? And so we have, again, sort of color coded, so red versus pink, green and blue. And what you'll notice is that the red one, right, is always on the left, the green one is at the top, edge, the pink one on the right edge, and then the blue one at the bottom edge, right? And what you see is the domain walls between them, right, get pinned right at the corners, right? And so sort of the schematic that we came up with is that, you know, we have these domains, they're canting out of plane, right? And then the domain walls want to cant or want to pin at the edges. And so we get this edge preferred orientation of the antiferromagnetic spins. And in the center, you basically get just random domains, which don't really care about what's going on at the edges. But we can get sort of over about a 300 or 400 nanometer range, we can get this region where we can use the shape of the nanomagnet in order to sort of dictate what the local antiferromagnetic spin structure is. And what we did is that just to confirm that we have, you know, made the right assignment of our antiferromagnetic spins, what we did is we rotated the sample by 45 degrees. And so then, and then repeated the experiment. And again, we're able to sort of bin our 4 different types of domains, again, showing again that we have this preference for these, you know, different colors to lie along the edges, right? So using that, we have this shape anisotropy. Okay, so this is now, you know, for when the edges and the nanostructures were along the 1, 0, 0 directions, right, which are sort of the easy axes for the antiferromagnetic spins. And then what we did is we tried a whole bunch of different shapes, right? And so now we have different shapes, which many of the axes, right, are not along these easy axes, right? And so we had this series of different types of domains. Again, we can bin them, right? I won't show you all these curves for all different shapes, but we could do this sort of binning for all of them to characterize where the locations are. And so we got some interesting effects. So if we had the pentagons and the circles, right? So basically almost none of the edges are along the easy axis. We get all the really small domains, right? And they're sort of random and they don't really have a preference for any of the edges. But then if we went to these triangle regions where we have very few sides, right? And at least one of the sides was along one of our easy axes, then we actually see that we get, you know, the filling of the shape through most of, which is a very few number of domains, right? So we really basically only get 3 domains in the triangles, right? Whereas we get many, many, many domains once we start having more edges to it, right? So again, showing that we can sort of control antiferromagnetic spins through the shape. So that was for sort of a fairly thick antiferromagnetic layer. And so, you know, what we also had was a sample where we grew a superlattice, right? So this is an LSMO LSFO superlattice. So individually, the layers were 6 unit cells in thickness. And so what happened with the sample, which is, you know, so maybe a little unexpected, is that the Néel temperature was fairly high, still above room temperature, but the Curie temperature dropped quite a bit, which meant that we could have a temperature, you know, at room temperature where we only had an antiferromagnetic layer. So basically at a sample where we're only looking at ultra thin antiferromagnetic material. So even at 6 unit cells, this material was still antiferromagnetic. And so then we took a look at the images. And so this is, you know, one image that we have from this. And now you can see that we have a much simpler domain pattern that we had before when we were just looking at one thin film, right? And basically only having 2 types of domains, right? So we don't get the 4 domain binning, we only get 2 types of domains, right? And so again, we can map these out, right? And so what was black is now showing up as, we've binned it as green, and then the white shows up as pink. And then you can see that we have these gray domains at the borders, which we can't really bin. And so those are the domain walls themselves, right? And so now we only get 2 types of domains, right? And interestingly enough, then these domains are such that they always want to be perpendicular to the edges of the nanostructures, right? And so we get sort of this sort of anti, you know, well, I don't know, you know, they want to be perpendicular to the edges of the nanostructures. They want to lie along the 1, 0, 0 directions. And then what's also different from the thin films is these are now completely in plane. There's no canting angle for them. So somehow the in plane or the thin film nature basically pins these antiferromagnetic planes to lie completely in plane. And so then again, what we did is, look at different shapes, right? So this is your diamond, or the ones where we've rotated them. So now the edges are along, nominally the hard direction for this antiferromagnetic material. And so now what you can see is that there are very sharp contrasts in the center. And then the thing, the regions along the edge, right, are sort of uniformly gray, right? And again, what we did is bin them. Now we get 4 different types of domains, right? And then what we see is that in the center, right, we get what sort of our easy axes, right, domains, which are following the same directions that we saw for the previous example, right? So just those green and pink domains. And then the edges, there's a small region at the edges which we could bin as blue and yellow, right? And so now again, these are completely in plane, but the antiferromagnetic spin axis wants to lie again perpendicular to the edges of the nanostructures. Right. And so if we sort of compare then, what we are seeing for the ferromagnetic and antiferromagnetic domains, right, is that again, we sort of see the similar effect that the center part wants to follow the orientation of our magnetocrystalline anisotropy, and then the edges will follow shape anisotropy. But for ferromagnetic materials, because we have that magnetostatic energies, then the perimeter part wants to be parallel to the edges of the nanostructures. But in these ultra thin micromagnets, then we are getting them to lie perpendicular to the edges, which is sort of interesting. So again, showing that we can use patterning as a way to dictate our antiferromagnetic spin axis orientations. Okay, so then what I want to do is just sort of show quickly some examples now where we can actually have coupled ferromagnetic and antiferromagnetic structures, right? And so in this case where you have a ferromagnetic antiferromagnetic interface, then the typical sort of exchange coupling interaction that we see is exchange bias, right? So in this case with exchange bias, if you've got strong exchange bias, you can actually get the horizontal shifting of your hysteresis loop away from center, right? And so this kind of exchange interaction then usually occurs in what we might refer to as an A-type antiferromagnetic material, where you have all spins in one direction in one layer, and then followed by all spins in the opposite direction, right? And that's how then you can get this biasing of the ferromagnetic layer by the antiferromagnetic layer, right? But then the question is, what happens if you have a G-type antiferromagnetic material? So our LSFO is a G-type antiferromagnetic material, where if you look at one iron atom, right, so say this red one, then all its nearest neighbors, right, and I removed the lanthanum, strontium, and oxygen ions. These are just your magnetic iron atoms. All its nearest neighbors are anti-parallel to each other. So what happens is that now, if we look at our 1,0,0 surface, you have an equal number of these blue and yellow, or blue and red spheres, which means we basically have an equal number of opposite exchange interactions. And so basically the system gets frustrated, and instead of having that horizontal shifting of the hysteresis loop, then the system minimizes its energy by having a perpendicular orientation between the ferromagnetic and antiferromagnetic layer, which is known as spin flop coupling. And so this is, somewhat more difficult to analyze, at least through hysteresis loops, because you don't get that horizontal shifting of the hysteresis loops. You might just see an increase in the coercive field because of the pinning still that you have with the antiferromagnetic and the ferromagnetic layer. And so, we wanted to look for this, what kind of exchange interactions we might have. So in this case with a bilayer structure, so we have a fairly thick LSMO layer at 9 unit cells, 10 unit cells of a ferrite layer. So in this case, it's just the pure lanthanum iron oxide. And so if we look at our first look at the ferromagnetic layer, so the LSMO layer, right, we pattern them again in 2 micron squares. And so what I show you are a couple of different squares, because you can see that they all have sort of different patterns, right? The one here in the top left sort of is that Landau pattern that we're expecting. This one down in the bottom right somehow is still a Landau, but at the core is shifted, right? And then we get these other interesting structures, which we kept calling Zorro domains because they look like the letter Z, right? And so these are ferromagnetic domains. So something is changing, right, in our ferromagnetic layer because we have this antiferromagnetic layer next to it, right, or directly on top of it. And then we could, tune to the iron absorption edge, change to linearly polarized X-rays, and look at what are the domains that we get in the antiferromagnetic domain, right? And you can see that they basically map one-to-one, right? So we get the Landau pattern, we get this bow tie pattern in the antiferromagnetic materials, you can get the Z in the antiferromagnetic domains, right? And so what we did is then do the analysis of the antiferromagnetic domains, right? And we can actually see that we always get this perpendicular orientation between the antiferromagnetic and ferromagnetic layers, right? So we're getting spin flux coupling, right? At least regardless of all these domains, right? So that was, we could see from Peem. And then we were sort of puzzled as why do we get this offset of the center of the vortex cores? Why do we get these Zorro domains, right? And so again, we did some micromagnetic simulations. And what we could always tell from these is that then the ferromagnetic domains have a net magnetization along the diagonal of the nanostructures, and it was basically random depending on which nanostructure we looked at, right? So sometimes it was going up to the right, sometimes down to the left, right? It basically was, there was no set direction, so we know that it wasn't because there was a magnetic field induced, in the microscope or some anisotropy in the sample during construction. It's really something that's inherent, right? And we could also then basically, get these kinds of domain structures to arise by, again, having this local field, which we think is an exchange bias field, right, which wanted to lie along the diagonals, and they were just, would just randomly appear depending on which micromagnet we have. So it's sort of an interesting case where we get both the simultaneously spin flux coupling as well as exchange bias, right? So both of those types of exchange coupled interactions were occurring in the system. And then the last one that I wanted to show is just, again, going back to the sample where we had the LSMO micromagnet. So before we were looking at room temperature, we cooled the sample all the way down to 36 Kelvin, which is now below the Curie temperature of the LSMO layer, right? And then we got these kinds of structures. So on right is the ferromagnetic domains, on the left is the antiferromagnetic domains. And so what we were able to see is that there still is correlation between the ferromagnetic and antiferromagnetic domains, but now because the layers are so thin, now the ferromagnetic domains are extremely thin, right? So we see that in thin films as well as that the domain size will scales with the thickness of the film. So that's also what's going on here. But then they're locally then still maintaining this perpendicular orientation. So spin flux coupling is still taking place. And then what also was sort of interesting is if I looked at exactly the same micromagnet at room temperature versus these cryogenic temperatures, right, then we can actually see that the antiferromagnetic domains are actually changing the position of their domain walls with temperature, right? So that actually means that antiferromagnetic domains can reconfigure, which is sort of interesting because people sort of say, oh, antiferromagnetic domains should be pinned at defects, right? But we can actually start moving them around, right, with different conditions as with the coupling with our ferromagnetic layer. So what I'll do is one last thing that I wanted to mention before end is that, so where is this work going, right? So what can we do with the fact that we can control the antiferromagnetic spin axis? So we've been working with Barry Zink's group at the University of Denver. And so he can do some of this non-local spin transport measurements. So basically using the inverse spin Hall effect. And so he patterns some of these electrodes on the sample. So this is an optical microscopy images of one of the patterns that he has. And I don't want to sort of go into too much detail about the measurements, but the idea is, basically, if we can control the antiferromagnetic spin axis to be sort of parallel or perpendicular, right, to the positions of the axes and the direction of spin flow, can we actually sort of, characterize that anisotropy in the material? And this basically follows on some of the work he's been working on already with amorphous germanium. So it's proving that at least this measurement technique works. And so we're sort of working on that now with these complex oxide systems. So then I'll just end with this last slide as the summary. So hopefully then what I've shown you today is that perovskite oxide multilayers are sort of a rich playground, right? Where we can use a number of different parameters, so structural, chemical, magnetic, electronic interactions to finally control the functionality of these materials. And, patterning of these materials and using our XPEAM analysis, right, allows us to show that we can manipulate not only ferromagnetic domains, but also antiferromagnetic domains. And it really occurs through a balance of different magnetic terms, including shape anisotropy and magnetocrystalline anisotropy. And, the PEAM, I think, is a really strong technique where we can, locally, right, extract parameters, right, of magnetic parameters of materials, nanostructures and microstructures, with sub-micron or sub-nanometer, 100 nanometer length scales, and do things as a function of temperature. You can also apply voltages, you can apply magnetic field pulses, so you can get, rich host of information, not just, pretty pictures out of them. And then the future work would be really being able to do these non-local spin transport measurements. And so with that, I'm going to end here, and then thank you for your attention, and I'd be happy to answer any questions.
Okay, thank you very much for this interesting talk. We can use the applause button under the reactions to thank Professor Takamura. I'll take over the Q&A from Shen because his internet connection is not stable. So if you have a question, please raise your hand in Zoom. It's also now under the reactions in the new version. If you're watching on Twitch, you can just type in your question into the chat box and I'll read it for you. Sha, please go ahead with your question.
Very nice talk. So this is Xiaohong from University of Nebraska Lincoln. I have a question about the kind of sensitivity and resolution of your technique. Mm-hmm. So we showed, so just to a little bit of clarification. So we showed that if we pattern LSMO on STL just into nanostrips, that's around 200 to 400 nanometer wide and 2 nanometer depth. And you can put the sample in a very strange non-equilibrium strain state so that the anisotropy actually can be enhanced by 10 times. I noticed that for your work, you are normally working around really thick films, like 100 unit cells. So, but for 2 nanometers, basically 5 unit cell, is that something you think you can resolve?
So I guess, so 2 nanometers is sort of the thickness, is your thickness of your film then, and you're just, and then you want to know whether or not you have enough sensitivity to measure the magnetic signal from PEAM. Is that your question?
So for our work, we actually have for example, a base layer. So it's a 6 nanometer film, continuous, but the top layer will pattern it into nanostrips, nanolayers. I mean, which means the base probably still in the normal strain state for LSMO and STL, but the top actually has different anisotropy.
Okay. So. Yeah. Okay. Now I remember the work. So yeah. So PEAM is electrons in and photoelectrons out, right? Which means then that, so we're actually not sensitive to the whole, even though we have 100 nanometer thick or 100 unit cell thick film, the photoelectrons don't, the X-rays can penetrate, but the photoelectrons can't leave from more than like the top 5 to 10 nanometers of the sample, right? And so that's also one consideration that you always have to make with these samples that you put in PEAM, is that you can't put any capping or many capping layers on top, because if your capping layer is say 10 nanometers thick, then you will only probe that capping layer, right? And so for our samples, we really are only probing sort of the top 5 to 10 nanometers, and we have no idea what the rest of the sample is doing, because the photoelectrons are not, or just don't leave the sample from there. So in your case, then, I guess, so, and it's all LSMO, right? It's just different stream state. So you would still be looking at, manganese from manganese. And so you would get the strongest signal from the top part of the sample, but you would not be able to eliminate what the rest of the film is, right? So it would be sort of a combined effect, but it exponentially decays as you go thicker, further down in the sample. So you would get the strongest part of the sample from that 2 nanometer layer. So that's fine. You just have to count longer, right? So, so maybe, you might have to count 15 seconds per condition, if for like one of my samples, but you might have to just increase the count time to get a good enough image, so maybe you need to go to 60 seconds just, per image, just to improve the image quality. But, so that's fine. But you are just in that region where you have those structures, you would get a convolution of the top layer and the bottom layer. And so if they're doing something completely different, then it might be really confusing as to what the structure is, magnetic structure is. The lateral resolution, right there, so it's like, so there's the resolution that you can actually see that something exists, right? So always the SEM resolution. If you want to know what magnetically that region, what magnetic state it is in, Andreas Scholl, who created the PIM3 microscope, always says you need to have 5 pixels in there. So sort of the, magnetic spatial resolution is always worse than the sort of SEM spatial resolution. And that somewhat depends, well, actually, it depends a lot on how conductive your sample is. So one thing that I didn't mention is in the PIM, in order to better capture all the electrons that come off of the sample, we apply something like 20 kilovolts to the sample. So that's fine if you have metallic magnetic materials, right? But if you have a sort of, these oxides are never very conductive, so we can never push that voltage as high. And so your spatial resolution for these complex oxides is worse. And especially for our case, with the way we pattern them, they become, not only do they become amorphous, they become insulating. So we have this really crazy insulating matrix, right? So which can sometimes distort our images. So if you're just sort of, those ridge features, then you might be better off and you might have better spatial resolution than what I have. So we've been able to say 100 nanometer spatial resolution for complex oxides that we pattern this way. But within metallic systems, they can get to smaller, maybe tens of nanometers.
So you mentioned that you may make the top layer amorphous. So you need to, does that mean you need some protection, like some capping layer? So
that's what we did sort of with the patterning. Yes, the way we pattern our films, right? So that, I don't know if I can go all the way back, but so our argon ion implantation is designed to amorphize the whole film locally. So we'll put down a chromium hard mask, and then the chromium hard mask then protects. So protects the part of the film that we want to protect, and then everything else around it gets bombarded with the argon ions, and then is non-magnetic, amorphous and non-magnetic. So depending on how thick the film is, then we'll tune the argon ion implantation energy. So a thicker film, we'll use a higher energy. For a really thin film, we'll use a lower energy, just to get sort of the projected range of the implant to be in the center of the film.
So that's actually in a fabrication part, right? So you don't, I mean, the measurement itself shouldn't.
Yes, the measurement itself should not do anything. Yeah, it's just X-ray. It should be a non-destructive process. That's X-rays in, electrons out.
Okay, great. Thank you.
Okay.
Okay, thank you for this discussion. Are there further questions? I think I saw a hand raised. If you still have a question, please raise it again. In the meantime, let me ask about that pattern that you discussed with the antiferromagnets, that the order parameter was orthogonal to the edges. Is there a model that explains why that is happening?
No, not that we know of. And I guess Yeah, not really. I mean, I guess unless, you sort of think that because you're alternating back and forth so that, shape anisotropy doesn't go away. I guess one thing is I should say is that magnetically, we don't really have a model, but I think maybe what we think is actually going back to the question about the patterning effect is that we think that it might actually be because of that surrounding matrix that we have here, right? So because we have this implanted matrix, right, it's swelling up vertically, which also means it wants to swell laterally. So what we think is that we're getting this maybe some kind of lateral strain field, right, sort of affecting the edge region, and maybe that's why we're actually getting an edge induced effect.
Yeah, this is what I was going to ask about, that you can have magnetostructural coupling, but then it might depend on the sign of the coherency strain. So you could engineer structures with a different sign and check if your pattern actually switches from orthogonal to parallel.
Right. Yeah. So we've only done this on strontium titanate substrates, and I guess I should say these are actually niobium doped strontium titanate substrates, and we do that because all the charging reasons that I was talking with Xiao about, is that it helps to have a conductive substrate. So if we can get a conductive substrate on a different substrate, then we could do that. But niobium doped SDO is the best one we have, so most of our work has been on those. Okay. But that is something, that we are sort of trying to figure out is that really an edge effect? And especially since we see that the magnetocrystalline anisotropy, right, is different at the edge compared to the center, right? So we're also wondering if that's something that's structurally, if they're all sort of related to each other, because again, it's sort of this few hundred nanometer length scale for both the edge effect, right, the loss of the magnetocrystalline anisotropy. So what we need to do is get, one thing is to try to do some kind of structural, very detailed structural measurement of these implanted samples to see if we can see those minute differences in structure.
By the way, do you know why the anisotropy depends on the position in that bit?
So again, our guess was this. It was the matrix, but and still something we're trying to figure out for sure.
You mean strain related?
Yeah, from the implanted matrix surrounding it.
Okay. All right. Thank you, Barry. Please go ahead with the question.
Yeah. Hi. Yayoi. Nice talk. As always, but this question I think is potentially related to the last one. When I was looking at these lovely patterns, it occurred to me to wonder if you'd ever tried to make a nanostructure that had some kind of hole in the middle, like so that you could have a ring or like even a triangle inscribed in a circle or something, to try to give you another knob to play with this idea of what the anisotropy does.
Good idea. Yeah, good point. We have not done that, so maybe we should do that on our next pattern. It's easy enough to do. So, yeah. Okay. I don't know why I never thought of that before. Okay. We'll next implant run, you'll put it in the CAD. So.
All right. Cool. That's it. That'll be fun.
And donuts. So.
Okay. Shen, would you like to ask a question? See you. Sent one through chat.
Yeah, I can ask just in case my Zoom freezes out again. Sorry, it's been very unstable at this moment. So you showed that with the Zorro patterns and the Landau pattern, seems that in the exchange coupled films, the ferromagnetic domains and antiferromagnetic domains are strongly coupled. So does it mean that if I can use an external magnetic field to rotate the ferromagnetic domain and in order to actually change the antiferromagnetic domain?
Yeah, so we haven't done it in the PEAM just because it's an electron microscope and you can't actually image with a field on. You can apply pulses, right? And then image in remnants. So with those, we definitely see that, yeah, both the ferromagnetic and antiferromagnetic domains change with the pulses. But we've also have done it with spectroscopy for unpatterned films and shown that, yeah, you apply a magnetic field and the antiferromagnetic spins to be, rotate to be perpendicular to that. So we're pretty confident that's what we can do. So that's, sort of, again, those measurements would vary. We're going to apply a different orientation in the magnetic field and, ideally rotate the antiferromagnetic spin axis. Yeah.
Do you have an idea on the time scale? Is it like on the nanosecond time scale for the limited by the ferromagnetic domain speed?
Yeah, we have not done that. I mean, any of these measurements are slow measurements because you're actually acquiring spectra. So yeah. So our measurements are all like minutes time scales for doing the measurement. So so we don't know. I don't necessarily. I don't know. I mean, antiferromagnetic spins rotating. I don't have. I don't
Thank you.
But yeah, I mean, it would be interesting to see if we can try to get a measurement that gives us time resolution on that.
Thank you.
If you can manipulate the antiferromagnetic domain state through the ferromagnetic handle, have you thought about playing with things like GMR heterostructures with this kind of control?
Yeah, so we have, so that's definitely something that we're, interested in doing. These complex oxides are always funny, though, is that you start sticking another layer on top and weird things happen. So, but yeah, that's definitely something, we want to work towards is doing that kind of thing.
Okay, thank you very much again. It looks like we're out of questions. Let's thank Professor Takamura again.